So this question says find all first and second derivatives of the following function. And so this, like I mentioned, this is a multivariable function. This is saying that z is our dependent variable and z is a function of x and y. So that means we have two independent variables, x and y, and one dependent variable, z. You can think of it as like two input variables, x and y, and one output variable, z. So someone has to tell you what the variables x and y, what those values are, and then you could tell them what the value of z is that corresponds to that. Whenever I'm asking for the first derivatives, what I mean is, what is the first partial derivative of z with respect to x? And what is the first partial derivative of z with respect to y? Then whenever I ask for the second derivative, I'm talking about the partial derivative of z with respect to x. Well, actually, sorry, I mean the second derivative of z with respect to x. And then also the second derivative of z with respect to y. And lastly, the second derivative of z. But this is what we call the mixed partial, because we're going to take the partial with respect to x and then the partial with respect to y, or vice versa. It doesn't really matter the order that you're doing those in. But there's two first derivatives in this case. And another way we could write this is like this, the little subscript, to talk about the first derivative with respect to x and y. And down here, we could write these like the little subscript with two x's for the second derivative with respect to x, the subscript with two little y's for the second derivative with respect to y, and again we could write it with a subscript xy for the mixed partial. But there's 5 derivatives that we're trying to find. Whenever I say find all first and second derivatives, it's referring to 5 different things. And for the partial derivative with respect to x, I'm going to pretend that y is a constant. I'm going to take the derivative with respect to x, we pretend y is a constant. So if y is a constant, then e to the power y is just a constant, and the derivative of x is just 1. And so I can write this e to the y for my first term. And then again, pretending y is a constant, that means y squared is just a constant. The derivative of natural log of x would be 1 over x. And so I could write that as my partial derivative with respect to x. We're just pretending that y is a constant number. If it helps you, just say that y is the number 5, and then take the derivative pretending y is the number 5, and then when you're done, just remember that that 5 represents y, right? Because, well, whenever we're taking the derivative with respect to y now, we're going to start from the same function, but we're going to pretend that x is a constant. Like if we just pretend that x is equal to 5 for a moment, this equation would be 5 times e to the y minus y squared, natural log of 5. And so natural log of 5 is also just a constant. And so taking the derivative of this with respect to y would give me 5e to the y, because the derivative of e to the y is just e to the y. And then I would have y squared, which would be 2y natural log 5. But again, that's not really a 5. I was just using the 5 to help me pretend that x is a constant, right? So instead of having the 5, it's actually an x. That's what I mean when I say pretend x is a constant.
Oh, I got that one. Sort of right.
As you, whenever you're taking the derivative with respect to y, you treat x like it is a constant. Whenever you're taking the derivative with respect to x, you pretend y is just a constant. Okay, so for the second derivative with respect to x, we're going to start with the derivative with respect to x, and then we're going to take another derivative with respect to x. And that means pretending that y is a constant, so this constant term e to the y just goes away, and then 1 over x, that's going to be the same thing as x to the negative 1 power. And I like thinking about it this way because I can use the power rule, and x to the negative 1 power becomes negative x to the negative 2 power. And so I can write this as y squared x to the negative 2. So the y squared stays there because I'm pretending that y is a constant multiplier. The power rule says that I should multiply that second term by a negative 1. And so where this term was negative, when I multiply by a negative 1, it will become positive. And then the power rule for my derivative tells me that I subtract 1 from the exponent on x, and so that's why it's x to the negative 2 power. Another way I could write that is y squared divided by x squared, because that negative 2 power means I move it to the denominator. Then the next part is I need to find the second derivative with respect to y. So I'm going to start from this first derivative with respect to y, and then take another derivative with respect to y. And the derivative with respect to y means I pretend that x is a constant, and so that x is going to stay there as my constant multiplier, and the derivative of e to the y should just be e to the y. So then, since x is a constant, natural log x is just a constant, the derivative of y would be 1, so this is going to be minus 2 natural log x. So the last thing is the mixed partial. And that means I can start from my derivative with respect to x and then take another derivative with respect to y. Or I could start with my derivative with respect to y and then take a derivative with respect to x. Either way, I should get exactly the same answer, whether I'm doing this green route by taking the derivative with respect to y first and then taking the derivative with respect to x. Or if I do this orange route and I take the derivative with respect to x first and then take the derivative with respect to y, it's going to give me the same answer regardless. So like I mentioned last time, that's actually a good way to check your work. And so I'm going to do it both ways. I'm going to start with the derivative with respect to y and then take the derivative with respect to x. So starting from this and taking the derivative with respect to x, I pretend that y is a constant, and so that first term becomes just e to the y because the derivative of x would go to 1. So it would be 1 times e to the y. And then the derivative of natural log x would be 1 over x, and I pretend that the y is just constant, so I get something like that. Okay. What if instead I had started from this expression and taken the derivative with respect to y? So the derivative of e to the y would just be e to the y, and then this would be minus 2y times x to the negative 1 power, and you can see that I got the same answer regardless of which order I took the derivatives in. So when you're talking about the mixed partial derivative, it doesn't actually matter what order you take that derivative.
Sorry, it takes like 13 minutes to get here, and I woke up right at 9:30.
We just finished going over the quiz. Cyrus or Deanna, do you have any questions about the quiz?
Is this going to be expected on our final?
Yeah, definitely.
Yeah. Because I wasn't here.
Yes. So, for those of you that just came in, your quiz question today just asks you to find all first and second derivatives. And if you see a question about all first and second derivatives of this kind of function, where I have a dependent variable z, and it's a function of two independent variables, x and y, then that means there's going to be two different first derivatives you could take. You could take either the partial of z with respect to x or the partial of z with respect to y. And then there's actually going to be 3 different second derivatives you can take. You can take the partial of z with respect to x. Well, sorry, I mean the second partial of z with respect to x. You could take the second partial of z with respect to y, or we could take that mixed partial that we had talked about. And remember, with the mixed partial, it doesn't really matter if you take the derivative with respect to x and then the derivative with respect to y, or the derivative with respect to y and then the derivative with respect to x. You get the same answer both ways. And you can double check that.
I just have a question. On the second derivative for x, why did you pick the -2, x -2?
Yep. Okay, so what we did there is we started from the first derivative with respect to x, which is right here, and then we took another derivative with respect to x of that. So the e to the y, I don't see any x's there at all. And pretending that y is a constant means e to the y is a constant. And in the derivative, the constant just goes away. For the second term, I have negative y squared, which is just a constant, times x to the -1 power. And my derivative power rule would tell me that x to the -1 power becomes -1 times x to the -2 power. Because in the derivative power rule, you subtract 1 from the exponent, and you multiply by the old exponent, in this case -1. Yeah. Good question?
That was on me.
Good question. Okay, so again, if you just came in, I'll upload a video of this so you can copy this later if you want to for that quiz. Our new topic for today is we're going to talk about the extrema, which extrema just means maximums and minimums. How do you find the maximums and minimums? This would be important for like optimization questions. You know, like every business wants to optimize profit. Every business wants to, maximize profit. Every business wants to minimize costs, right? Whenever you say maximize or minimize, we're talking about, having an optimum choice of independent variables. And we talked about this before. In sections 12.1 through 12.3, we talked about finding maximums and minimums. We've kind of already done this. But in chapter 12, we were talking about single variable functions, right? So we said the critical points of a single variable function are the points where your derivative is equal to 0. If your function is smooth looking, right, so it doesn't have any angles in it and it doesn't have any discontinuities in it, as long as your function is smooth enough, then any maximum or minimum value has to be located at one of these critical points. So if you find a list of your critical points, that's a list of the potential places where you might find a maximum or minimum. Some critical points happen to be a type of critical point that's neither a maximum nor a minimum, though, right? There's some critical points where you have a 0 derivative, but it's not a maximum or a minimum, right? Like maybe your function is increasing, and then it levels off at a point your derivative is 0, but then it starts increasing again, in which case, no maximum or minimum. If your critical point has a second derivative that's positive, you have a positive second derivative, then that means you're talking about a minimum, because that would mean your function is concave out. If your second derivative is positive, that means you've got like a bowl shape, and so that critical point at the bottom has to be a minimum value. If your critical point has a second derivative that is negative, then that means that critical point is a maximum, because if your second derivative is negative, that means your function is concave down. It's got like that hill shape. And so the critical point at the top of the hill must be a maximum value. Now, if your second derivative is 0, then that doesn't really tell us anything. That means your critical point might be a maximum still. It could be a minimum, or it actually might be neither a maximum nor a minimum if you run into that situation. So the process of finding maximums or minimums would be to, determine the first derivative, set that first derivative equal to 0, solve the equation for x, and that would give you a list of critical points. And then you would want to find the second derivative of your function, plug in all of those critical point values of x, and determine if that second derivative is positive or negative or 0. And the value of the second derivative will tell you whether those critical points are minimums, maximums, or unfortunately in this case, it might not tell you anything, and you might have to do a little bit more digging into it to figure out what's going on there. So example 1 says find and characterize the critical points of the function y equals x cubed minus 3x. And so critical points are where I find the first derivative and then I set it equal to 0. So it's going to be 3x squared minus 3 as my derivative. And then if I set this equal to 0, then I can solve for x. And it turns out that x is going to be plus or minus 1. Right? Those would be my critical points. I have two critical points. One is x equals positive 1, and one is x equals negative 1. But it says find and characterize. And where it says characterize, I mean, is it a minimum? Is it a maximum? Or is it possibly neither? That's what I mean by characterize. And to be able to tell whether these critical points are a minimum or a maximum, I have to find my second derivative. And my second derivative means I take the derivative of the derivative, and so that would be 6x. And then the minus 3 goes away, so I say 6x is my second derivative. What if I plug in my positive 1 critical point, because that's one of my critical point? It would be positive 6. And if I plug in to my second derivative my negative 1 critical point, that would be 6 times negative 1. So that would be negative 6. So at x is equal to positive 1, that gives me a positive second derivative. And a positive second derivative means my function is concave up. So it's a bowl shape. So that critical point at the bottom of that bowl has to be a minimum. And when x is equal to negative 1, my second derivative is negative, so that means it's concave down, which means it has that hill shape, and the critical point at the top of the hill must be a maximum value. So for single variable functions, finding the critical points means finding the first derivative and setting it equal to 0, and then determining whether those critical points were maximums or minimums meant finding the second derivative and then plugging in the critical points to see if that second derivative is positive or negative. So this is what the function x cubed minus 3x looks like. This is your example function. And whenever x is positive 1, sure enough, it's concave up. And so a concave up function means that the critical point there must be a minimum value. And when x is equal to negative 1, sure enough, it's concave down. And so the critical point there has to be a maximum value. So this is, again, this is still a review of chapter 12. So hopefully this is a good refresher. Let's do number 2. Number 2 says, find and characterize the critical points of the function y equals x to the 5th power. And the critical point means I take the first derivative, and then I set that equal to 0, and I solve for x. And if I divide both sides by 5, I get x to the 4th equals 0. And so that means x has to equal 0. That's my only critical point. Characterizing the critical point means I take the second derivative. In my case, that would be 20x candidates that might be maximums or minimums. But just like before, some critical points are neither a maximum nor a minimum. And there's going to be a whole new phenomenon in multivariable functions that we call saddle points. And you won't find any saddle points in single variable functions. Saddle points only show up in multivariable functions. So let me show you a few things. If I can get the graphing calculator to load today. Sweet. Okay. So again, this surface represents a multivariable function. You tell me an x value and a y value, and then this surface maps that x and y point in the plane to a z value on that vertical axis. And clearly there's a maximum value, and the maximum value of the surface would be at x equals 0, y equals 0, right there. And if I wanted to make this into an example that has a minimum value, here's another surface where the minimum value is clearly down there, right, when x is 0 and y is 0. So this is kind of like a bowl shape. So that is just, if we found our list of critical points here, this would be a critical point, and then I'll show you what the test looks like to determine that's a minimum here in a second. But saddle points, that's what I want to look at right now. So yeah, let's get that one. This thing looks like either a horse's saddle or a potato chip, right? And this point in the middle, at x equals 0, y equals 0, in the very center of this little surface. That's what we call a saddle point, because in one direction, in the y direction, that would be a minimum value. You see, looking at the top of that, how that's a minimum value. But in the x direction, that point looks like a maximum value. So the same point, depending on which perspective you use, is either a minimum or a maximum. And so this is what we call a saddle point. And you can probably see why you don't get this in a single variable function, but it does show up in multivariable. Just like before with single variable functions, though, it's possible to have a critical point that's not a maximum, it's not a minimum, and it's not a saddle point. And so I have to think about this for a minute. But if I have x cubed plus y cubed, I think that does the trick. Yeah. So it might be difficult to tell because this is a little bit darker than I want it to be. There we go. But this point at the origin, at x is 0, y is 0, it seems to be like in the y direction and x direction, you're sort of increasing in function value as you approach 0. And then also in the x direction and the y direction, the function's increasing after that. But if you zoom in really close to that point, the slopes or the derivatives do get flat. They do go horizontal, so you do have a 0 derivative in both directions there. It just makes this kind of weird shelf in the face of this kind of cliff. So you can have points that are maximums, minimums, saddle points, or none of the above after you find your list of critical points. So this next box down here says, if you want to actually be able to characterize critical points of multivariable functions, you want to find out, is it a maximum, is it a minimum, is it a saddle point? This is the test that we're going to use to figure out maximum, minimum, saddle point. We're going to make our list of critical points, and a critical point is going to have both an x value and a y value for a multivariable function. And then we're going to find all of my second derivatives. Right? So we have the second derivative with respect to x, the second derivative with respect to y, and the mixed partial, which is the derivative with respect to x and then the derivative with respect to y. And then we're going to evaluate all three of those at the critical point, a comma b. So that's saying that my x value is a and my y value is going to be b. I'm going to evaluate those there, and then I'm going to multiply these two and then subtract the mixed partial evaluated at the critical point squared, and we're going to call this value that we get capital M. And there's 4 possibilities. Either M is positive and your second derivative with respect to x is negative, and in that case you're talking about a local maximum. If M is positive and the second derivative with respect to x is positive, then that function is a local minimum at the critical point. If M is negative, then that critical point must represent a saddle point. And if M is equal to 0, then we don't know. Maybe it's maximum, minimum, saddle point. Maybe it's none of the above. So it is a little bit more complicated than the single variable case. However, it still sort of looks like the single variable case. Critical points is still a manner of finding the first derivatives and setting them equal to 0. And whenever we try to characterize critical points, we still end up finding the second derivative and figuring out if it's positive or negative. It's just that with multivariable functions, you have 3 different ways you could take the second derivative, and you have to account for all 3 of those. All right, so let's do some examples. Like example 3. It says we want to find and characterize the critical points of the function blah, blah, blah. And in this process, whenever you're asked to find and characterize, finding the critical points means I'm going to have to calculate the 2 first derivatives. And then characterizing them means I'm going to have to calculate my 3 second derivatives. So just like our quiz today, I actually have to find 5 derivatives before I start to answer this problem. So let me first take the partial derivative with respect to x of this function. We'll name it f. And the derivative with respect to x means I just pretend y is a constant, right? So my first term is a constant, it goes to 0. My last term is going to be practically a constant, so that goes to 0. And then the middle term, 1/2 x squared, the derivative with respect to x is going to be just x. Not too bad. If I take the derivative with respect to y, then my first 2 terms are basically constants, because we're pretending that x is a constant. My last term is going to become negative y because of the derivative power rule. If I take the second derivative with respect to x, that's going to be positive 1, right? If I take the second derivative with respect to y, that would become negative 1. And if I take the mixed partial, that means I can either start from here and take the derivative with respect to y, or I could start from here and take the derivative with respect to x, and I should get the same thing regardless. Well, the derivative with respect to y, if I pretend x is a constant, that's 0. If I take the derivative with respect to x here and pretend y is a constant, that should be 0. So my mixed partial is going to be 0. Okay, so I found all of my first derivatives and all of my second derivatives. My critical points. How do I find the critical points? That means I take my first derivatives and I set them both equal to 0. So that is going to say x is equal to 0. And this tells me that negative y is equal to 0. Which also tells me that y is equal to 0, right? So I have one critical point. And that critical point is when x and y are both equal to 0. So basically the origin on the xy plane. That would be my critical point here. if I want to characterize my critical point, that means I have to calculate this m value, which means I have to figure out what is the second derivative with respect to x evaluated at my critical point times my second derivative with respect to y evaluated at my critical point minus my mixed partial derivative x and y evaluated at my critical point all squared. So my second derivative with respect to x is just 1. My second derivative with respect to y is just negative 1. And then my mixed partial is just 0. So my value for m is going to be negative 1. And if my value for m is negative, that tells me we're talking about a saddle point. Any questions about that example? I figured out it was the saddle point, that little test. Okay, let's see what this looks like. If I have 1 plus half x squared minus half y squared. 1 plus half times x squared minus half times y squared. Yep, that's what that surface looks like, and sure enough, at the point x is 0, y is 0, there at the origin, that does look like a saddle point. So our math checks out. Example 4 says, find and characterize the critical points of that function. So if we're trying to find critical points, I have to set my first derivatives equal to 0. And those first derivatives are going to be negative x, and the first derivative with respect to y is going to be negative y. My second derivative with respect to x should be negative 1. My second derivative with respect to y should be negative 1. And then my mixed partial, like before, should be 0. So again, looking for my critical points, that tells me that negative x is equal to 0, which tells me that x has to be 0. This tells me that negative y is equal to 0, which means y is 0. So that gives me one critical point, because I have to have the point be 0, 0. If I want to characterize the critical point, I find m, which should be my second derivative with respect to x evaluated at my critical point, times my second derivative with respect to y evaluated at my critical point, minus my mixed partial evaluated at my critical point squared. So that's -1 times -1 minus 0 squared. So this time m is positive. If m is positive, then this could be either a maximum or a minimum, right? According to my little box on the second page of your notes. So then the next question asks is, what about your second derivative with respect to x? Is it positive or negative? And if m is positive and the second derivative with respect to x is negative, then that means we are looking at a maximum. So considering both of those things and looking at your table right here, m was greater than 0, but the second derivative with respect to x was less than 0, so we had a maximum. Okay, so let me know if you have any questions about example 4.
Wait, how did you find the maximum? Or what did you do?
So finding the critical points means you take the first derivatives and you set them equal to 0. So these were my first derivatives, and when I set those equal to 0, I found my critical point was at 0, 0. So if you have a maximum or a minimum or a saddle point, it has to exist at a critical point. You won't find maximums or minimums that are anywhere besides critical points. So your list of critical points is a list of candidates that might be maximums or minimums or saddle points. Then to figure out whether or not this critical point is a maximum or a minimum or a saddle point, we do our little m test where we calculate m. And since we found that m was positive 1 and the second derivative of x was negative 1, we're talking about this first bullet point, and this first bullet point tells me that that test told me I have a maximum at my critical point. So I have a maximum of this function at the point 0, 0. Let's look at this really quick before we move on. So I've got 2 minus half x squared minus half y squared. So that's what my surface looks like. And sure enough, there's a maximum at the point 0, 0. All right, so example 5. Just make sure everything checks out. I know that in these first few examples, like the derivatives are intentionally very easy to take, right? I'm not throwing anything at you larger than just like x squared or y squared. That doesn't mean you might not see anything more complicated than this. I just want these examples to illustrate what a min-max saddle point looks like when you find it. I have slightly more complicated examples at the end, if we get through the end here. So critical points means I set the first derivatives equal to 0. My first derivative of this function with respect to x would be x. My first derivative of this function with respect to y would be y. My second derivative with respect to x would be 1. My second derivative with respect to y would be 1. And my mixed partial is going to be 0. So then these are going to give me x equals 0, y equals 0, which is again just one critical point at 0, 0. What about characterizing them? Well, M is this formula we've been using. So I'm looking at 1 times 1 minus 0 squared. So M is positive 1, which means I either have a maximum or a minimum, according to my little table. My second derivative with respect to x is positive. So that means that I'm actually looking at a minimum. So that critical point I found at the origin has to be a minimum. I'm going to move on because I want to get through the rest of the examples. There's like 5 more. What if my function is z equals x times y? Well, the first derivative with respect to x, pretending that y is a constant, would be y. The first derivative with respect to y, pretending that x is a constant, gives me x. The second derivative with respect to x would be 0, because I pretend y is a constant. The second derivative with respect to y, pretending x is a constant, would give me 0. But my mixed partial, either way I look at it, my mixed partial is the number 1.
Wait. So, can you go up again on the first one?
Just the previous example, or?
Yeah, why does the... Go back now?
Okay.
Is it because they're connected that we're not, that we like take it, the derivative of it? So instead, last time we had f of x is equal to x, now it's f of x is equal to y. So we just take the...
So the rule whenever you're taking the derivative with respect to x is you just pretend y is a constant. It doesn't really matter what it is. So we could pretend that y is 42. Right? So this would become z is equal to x times 42. And taking the derivative with respect to x, well, that would just be 42, right? Because the derivative of x is 1, and you keep the 42 around because it's 1 times 42. So that was just for pretend, and so really the derivative with respect to x would be y, right? So y isn't actually 42, but we're just pretending that y could be any constant, and we treat it like a constant whenever we take the derivative with respect to x. Then whenever we take the derivative with respect to y, we pretend that x is a constant. And so you were looking at a constant times y. The derivative of y is just 1, and so then you keep x, pretending that it's constant. Okay, so critical points, finding them means I set the first derivatives equal to 0, which gives me y equals 0 and x is equal to 0. So we really haven't been very creative with our critical points yet. Because I only have one critical point at the point 0, 0 again. If I wanted to characterize what type of critical point is this, is a minimum, maximum, saddle point, I have to do my M test. My M test says I take that second derivative at my critical point times this second derivative at my critical point minus my mixed partial evaluated at my critical point squared. And so m is going to be 0 times 0 minus 1 squared. And so m is going to be -1. And since m is -1, that tells me we are looking at a saddle point. If you have a negative value for m, you're looking at a saddle point. So what do we get if we plot x times y? Sure enough, that's definitely a saddle point. Okay. On example 7. We want to find and characterize the critical points of that function. So we'll find all of my first and all of my second derivatives. Derivative with respect to x is going to be what?
3x.
Yep. Derivative with respect to y should be
3y.
nice. The second derivative with respect should be
6.
and my y.
6y.
What about my mixed partial?
0.
Yep, thank you. So in the mixed partial, I look at my derivative with respect to x, and then I take the derivative with respect to y, pretending that x is just a constant. So if x is a constant, 3x squared is just a constant, and so in the derivative that goes to 0. My critical points are going to be the solutions to this system of equations. So that tells me 3x squared is equal to 0 and 3y squared is equal to 0. So again, I know this has not been very exciting, but my one critical point is at the point 0, 0. What about characterizing? Gotta do this whole thing. Oops. And if I take the second derivative with respect to x, which is 6x, and I plug in x equals 0, y equals 0, that would be 6 times 0. And then the second derivative with respect to y is 6 times y, but I plug in x is 0, y is 0, and I get 6 times 0. The mixed partial xy is going to be 0 all the time, so that's 0 times 0 minus 0 squared, so m is equal to 0, and this test is inconclusive. And that just means that we have no idea whether that point, that critical point at the origin, it might be a maximum, it might be a minimum, it might be a saddle point, it might not be any of those things. Could be something totally different. It could just be a regular old boring critical point. And if we look at x cubed plus y cubed, sure enough, that's the example I showed you from earlier, where it's not a saddle point, it's not a maximum, it's not a minimum, it's just a boring little weird flat part of the surface. Okay. So there's your example where m turns out to be 0. And so you've seen by now an example of all of the different ways that this m test could show up for a maximum, minimum, saddle point, or inconclusive. Still got a couple more examples to do. 3 more.
Question.
Yep.
So is the critical point always 0, 0?
No. You might have a different critical point. I hope there's one that has a different critical point. I haven't actually worked these problems yet, so maybe or maybe not. We'll see what happens in example 8. I know I'm going to have to take all of my first derivatives and all of my second derivatives. Whoops. All right, y, and then xy. So if I look at that function and I take the derivative with respect to x, what should that be?
3x.
There is going to be a negative 3x squared in there because you're looking at the minus x cubed, so that 3 comes down and becomes a negative 3x squared. What about this first term? It says 9xy. If we take the derivative with respect to x, that should be
9y.
awesome, yeah. 9y minus 3x squared. And we were pretending y is a constant and 6 is a constant, so those terms don't matter. If I take the derivative of that function with respect to y, I should get
Minus
perfect. 9x minus 3y squared. What about the second derivative with respect to x?
9 minus 6x. Or 6 minus
It's going to be negative 6x, and the 9y is going to go away because we're pretending that y is a constant. When we take the derivative with respect to x, we pretend y is a constant. And then what about the second derivative with respect to y?
negative 6y.
Yep, Dan is right, because we pretend that x is a constant whenever I'm taking the derivative with respect to y. What about my mixed partial? I think I heard it, yeah. It's going to be 9, because whether you're taking the derivative with respect to y of the derivative with respect to x, or the other way around, you get 9 either way. So, critical points, that means I set my first derivatives equal to 0. And if I set this first derivative with respect to x equal to 0, that's going to give me 9y minus 3x squared equals 0. And if I set the first derivative with respect to y equal to 0, that's going to give me 9x minus 3y squared equal to 0. So we're going to have to simplify this just a little bit. I'm going to divide both equations by 3. And so if I rewrite these guys down here, the first one's going to be 3y minus x squared equals 0. The second one will be 3x minus y squared equals 0. So the equations are still balanced because 0 divided by 3 is still 0. I need to solve this system of 2 equations, and I have 2 unknown variables, x and y. So substitution is a lot of times an easy way to do this. So I'm going to first solve for y here. And if I add x squared to both sides and I divide both sides by 3, I get y is equal to x squared over 3. That's what my first equation is telling me. Now if I plug in this formula, y equals x squared over 3, into my second equation here, that would give me 3x minus x to the 4th over 9. Because I'm plugging x squared over 3 in where y goes, so that would be like x squared over 3 squared. And x squared squared would be x to the 4th, and 3 squared is 9. and the right side of this equation is 0. So let me multiply everything in this equation by 9, and I would get 27x minus x to the 4th equals 0. If I factor out an x, which would be my greatest common factor here, I get x times 27 minus x cubed is equal to 0. And this has one solution that's pretty obvious. One solution is that x is equal to 0, because 0 times anything gives me 0. But there's at least one more solution. I think there's only one more solution, because this little factor here is a cubic polynomial. Right? If I set 27 minus x cubed equal to 0, I would get x cubed is equal to 27. And if I take the cube root of both sides, that tells me x has to be 3. Cube root of 27 is 3. Okay. So there's actually two solutions for x, for my critical points. Either x is equal to 0 or x is equal to 3. At the location of any critical points of this function. I haven't found my y's yet, and that's because I was solving by substitution. So let me take this first equation again, and I'll plug in x is equal to 0 to get 3y minus 0 squared equals 0. And that tells me that y has to be 0. So let me write that out. When x is equal to 0, y has to be 0. Okay, so what if I take this equation again, and I choose my other value for x, which is x is equal to 3? Then I would have 3y minus 3 squared equals 0. So that tells me that 3y is equal to 9, or that y is equal to 3. So in other words, when x is equal to 3, then y has to be equal to 3 as well. And so based on these two things, that one and that one, I find that I have two critical points. One when x is 0 and y is 0, and I actually have another critical point when x is 3 and y is 3. I kind of run out of room to do my m-test, but we're going to try to characterize these critical points now that we've found them. I've got critical points at 0, 0 and 3, 3. Let's do the m-test, which is going to say calculate the second derivative evaluated at 0, 0 times the second derivative with respect to y at 0, 0 minus the mixed partial evaluated at 0, 0 squared. So if I take negative 6 times x and I plug in x equals 0, that becomes a 0. Looking at my second derivative with respect to y. Negative 6 times y, when y is 0, that's 0 as well. Minus my mixed partial squared would be minus 9 squared. So my m is negative 81 for my m value whenever I let the critical point be 0, 0. So at that point 0, 0, my m is negative, and if m is negative, I think that means it's a saddle point, right? Yeah. So I'm going to have a saddle point at 0, 0. And I still have another critical point, and I want to characterize my critical point at 3, 3. So I'm going to do that on the top of this next page, I guess. So calculating my m value at the critical point 3, 3 is going to look like this. And if I look at my second derivative with respect to x, that is negative 6 times x. If I evaluate that when x is equal to 3, that would be negative 6 times 3, which is negative 18. Second derivative with respect to y is negative 6 times y. So negative 6 times 3 is also going to be negative 18. Minus, my mixed partial is 9, and so I subtract 9 squared. So this m value is negative 18 times negative 18. So the two negatives make a positive. 18 times 18 would be 2 times 2 times 9 times 9, which would be 4 times 81, which would be, yeah, 324. And minus 9 squared, so minus 81. So m is definitely some positive number. Yeah, thank you, 243. Excellent. Since m is positive, I'm either dealing with a maximum or a minimum at that critical point. If I look at my second derivative with respect to x, that is negative. So I think that means I'm dealing with a maximum, right? Negative second derivative, positive m. That means that I'm looking at a maximum because that's that first bullet point for my m test. So at the point 3, 3, that critical point is a maximum. So this is a neat example. It answers several good questions. Like Chris asked a good question, is the critical point always 0, 0? No, you can have critical points other than 0, 0, like the point 3, 3 gave us a critical point here. It shows you that, in all our previous examples, it was really easy to find the critical point, but this finding the critical point required us to solve a system of 2 algebraic equations with 2 unknown variables. And so that was kind of tough. And also, we've got both a saddle point and a maximum, which might look kind of cool. So I'm going to try to plug this into the graphing calculator and see if we can look at it in our last minute before class is over. So I've got 9xy minus x cubed minus y cubed minus 6. So it's pretty difficult to see, but you can see it if you look really close. At the origin, x is 0, y is 0. Do you see how there's a saddle point? It's pretty low down there, but there is a saddle point. You see how it's a maximum in that direction, but it would be a minimum in that direction at that saddle point. So that's the saddle point at the origin we found. We also found that there was a maximum at x is 3, y is 3. And you can see that that peak right there, that would be that maximum we're talking about. Maximum value of that function. So you characterize those two critical points correctly. And that's it, because it's 10:50. So
Can you make it scroll down a little bit?
yeah.